Hi, today we're going to work through some more of the trends of the periodic table. You know the drill at this point. Feel free to pause if you want to answer these for yourself. I do suggest it. Link to a reference table above our heads. My head, at least. What occurs with the atomic number of the elements? What occurs as the atomic number of period 2 increases? So we're going from left to right. Nuclear charge decreases. Nope, that's not true. A nuclear charge decreases. Nope, it increases. And the covalent radius, also known as the atomic radius, decreases. Yep, small atoms over here, larger atoms over here. When an atom of lithium loses electrons, we lose electrons, so we're going to become a positive ion. And when that happens, the radius gets smaller. So to get started for today, the next trend, as it said on the title, was ionization energy. You know from your graphing activity that the ionization energy of alkali metals of any given group decreases as you move from top to bottom on the periodic table. The ionization energy will go up as you go from left to right, from metals to nonmetals. So we're going to delve into why, but I thought it might be nice to get just a frame of reference for how this looks practically.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly with air. Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
All right. Okay. Just the one thing I wanted to call attention to in that chemical equation, if you grabbed it super quickly, was that the sodium was going from no charge to a positive charge. So some conservation of matter says you become that way by losing an electron, and that's what I wanted to talk about, to not lose sight of. So in general, that I didn't define this because we've already talked about it, the ionization energy is the amount of energy required to remove the outermost electron from your atom. We're going to define it as ionization energy, but a lot of people call it the first ionization energy. It's kind of understood that if I say it, I mean the first one. And they are numbered having to do with which electrons are being removed, like first ionization energy, second ionization energy. You can remove more than one electron. But the idea is just to draw a quick picture of hydrogen. We know that if you absorb energy, the electron moves to a higher energy level, right? You get that excited state. So we're talking about a similar process, but we're talking about absorbing more energy. Like if you gave a lot of energy to this electron, hypothetically, it's just going to leave the atom completely, leaving behind just, a positive ion. In the case of hydrogen, that's just your nucleus. So in both of these cases, we're targeting this one electron that's way on the outside. This one being lithium, the same as before. This is rubidium. We saw both of those in the video. You saw that there was a reaction, and you saw that it was more vigorous with rubidium. So we can kind of draw that conclusion there, at least in this case, that a lower ionization energy yields more reaction. Okay, so that's our relationship here. Lower ionization energy, more vigorous reaction, bigger reaction. And I think that's kind of hard to connect together because we've got this energy and the reaction, how reactive, and considering all that. But in general, I just want to talk about the one step, not the reaction with water or air, where we remove the electron. So I want to make sense of these numbers. Seemingly a lower amount of energy is needed to remove an electron from rubidium than from lithium. In other words, it's less pull needed to get the electron out. When you see these numbers, it's kind of like how much you have to pay in to get out your product. So if we're going to talk about things like effective nuclear charge and size, we know this is a small radius. And from before, our effective nuclear charge is a +1. And for rubidium, this is a relatively large radius, and the effective charge is still a +1. So the effective nuclear charges on the valence shell, this is for the valence shell, in both cases are the same, so the radius seems to matter here. Larger electron means lower number. So I guess what you can kind of draw as a conclusion from this is that distance matters. The farther away the electron is, that yields an easier, it's less energy needed to remove the electron. So we can still tie that back to, it's far away because there are more occupied energy shells. And so that kind of makes it more space, and that's easier to remove. So in general, it seems like this is a comparison down a group. Down the group, that's a decrease, and that's why. As we go across a period, let's just remind ourselves from the numbers before. We've got +2, +7, and +4 as our effective nuclear charges. In this case, we've got two things to consider. We can say the number of shells, and we can say the size. Beryllium is relatively, we're just going to label them relatively, large. The fluorine is relatively small, and the carbon is relatively medium size. So if we were to rank them, the largest would be beryllium, the smallest would be fluorine. Well, we said before that size matters, and that the closer the electron is to the nucleus, the number seems to go up. And I see that here, but there's a much larger difference. It's almost double the amount of ionization energy to remove an electron from fluorine than from beryllium. So I think the other thing we also probably should focus on is this effective nuclear charge. So the two things that seem to matter is both size and effective nuclear charge. So small atom, but also larger effective nuclear charge causes stronger pull on the electrons, which would then yield a high ionization energy. So I guess if you wanted to look at it this way, you would predict that based on this ionization energy, that beryllium would be more reactive potentially than carbon when it comes to removing electrons. So that's also a good idea to keep in mind to tie it back to what we were seeing before. So our general trend, just to echo to what we saw before, this is a picture from your reference table, is that the ionization energy increases as you go from left to right across a group, and it decreases as you move from top to bottom. This means that we have lower ionization energies here, which, on the lower left-hand side of your periodic table, you have metals, and we have higher ionization energies here, which that would be mostly associated with nonmetals. There are some diagonal trends if you follow that, bottom left to upper right, just like before, but it's really hard to draw any sort of ionization energy trends in the upper left to lower right diagonal path. Of course, there's more layers. There's always more layers. So we have the graphs from before, but that was definitely some cherry pick data. Let's look at the full run of things and see what we can pull out of here. There are trends, but then there's kind of trends within trends. As we go across period 2 all the way from lithium to neon, a couple things stand out to me. First, the same trend is still there. There's a general increase from lithium to neon. But we also see these slight decreases. Wonder what's up with that. It might be worth, for this, starting to look at what the actual electron configurations are for some of these elements. So here are some of those electron configurations. I'm, of course, only going to worry about the valence shell, since first ionization energy refers to the first electron to come out, which is the outermost electron, which is the valence shell. I'm also going to circle the electrons that are going to be targeted, right? So technically, like, the last electron to come in is the first electron to come out. So let's take a look at which subshells these electrons are coming from. We've got 2s, we've got 2p for all the rest. Now, based on what we've talked about in class already, you might see a reason why nitrogen and beryllium would be slightly higher in ionization energy. These two, specifically, the removal of the electron involves breaking the half-filled or completely filled subshell. And we talked about in class that the half-filled or fully filled subshell invokes this like extra stability. It's a little bit better to exist like that, and I guess that's evident by this higher number, that breaking it would be harder. So that yields harder to break, which would be a high ionization energy. Well, higher, right? Everything is relative, and you can actually kind of see this benefit spelled out right here. How much higher? Well, it's a little bit, right? It's definitely not going to put nitrogen above fluorine or neon. This is like your relative size of that little tiny blip. Now here we can see that show up several times, but you can actually kind of see that it gets harder to spot when you're going from fully filled subshell to starting a new one, or half filled to like breaking that half full. And so like you can see that this diminishes. It's a small effect at most, but it is there, so that gives you a little bit of a view. Something else I thought that was kind of interesting is you can see that the things seem to level out a little bit as we go at, like, I circled the bottom and the top of each one, which is a quick way to find the groups, right? That's group 1 and group 18. It kind of shows me that like there's this leveling off effect, and I think there are two reasons for that. One, you'll notice that the distance between the repetition goes up, and that's obviously because each successive energy level can hold more electrons before you line back up with that valence configuration. But because you're dumping in all those electrons, we know due to the Aufbau principle, they're getting stuffed in the middle, right? This is filling 2s and 2p. This is filling 3s and 3p. This is filling 4s, 3d, and then 4p. And then this is filling 5s, 4d, and then 5p. And then over here we would be filling 6s, 4f, 5d, and then 6p. So in each case we're adding like more and more electrons, and when we add those electrons, by the time we get to the end, remember that we said these d electrons, they're higher in energy, but they're closer in radius. So there's actually a slight shielding effect. And so if you're adding a proton, but then you're also adding a slight shielding electron, you'll see that there are these regions where the change in ionization energy is relatively zero. And that's because the added proton and the added electron are almost canceling each other out, which is why the transition metals usually get lumped together. It's because the electrons that you're added are going to like an pseudo-inner level. Not pseudo-inner, but also pseudo-inner. It's very strange. But so you've got more and more protons, right? We're adding, 18 protons each time instead of adding 8. And you're adding electrons to the inner shells. So like you start to see this leveling off where the atoms that are really, really big are just not that different from each other, even when you're starting a new row. I mean, you still see, like, there's still this big jump between radon and francium and xenon and cesium, but over the course of the period, not as much changes as, say, from the second period. And then one final thing to mention. We had said at the beginning, and I, that when we say ionization energy, that we're always inserting this silent first ionization energy. But we don't have to. We could also talk about a second ionization energy and a third ionization energy. And what you can see on the table on the right here are some ionization energy values, kilojoules per mole, for the first, second, third, fourth, fifth, sixth, seventh for many of the atoms. But what you hopefully can notice if you look kind of closely is that there's a certain point on this graph where the numbers increase. So two things. First off, going from some atom X to X plus an electron, and then taking that X plus and then turning it into X2 plus an electron, this is higher. And then going from X2 plus to X3 plus is higher still. And that should be fairly intuitive, because to remove an electron from an atom that already has a surplus positive charge, remember we said those electrons next to each other, they don't shield effectively, but there is some shielding going on. So to remove an electron is to remove some shielding. And so the remaining electrons actually are pulled with more force towards the nucleus, and then it would make sense that you need to dump in more energy to get the next electron out. That doesn't explain why all of a sudden it jumps up, though. I think we can see if we look at sodium, and then its transition into a +1 and a +2 ion. Remember that the electron configurations, and we'll leave it at Bohr just to make our lives simpler, is 281 for the atom. That means that the electron that's coming out is coming from the third energy level, from going the atom to the +1 ion, but then it's coming from the second energy level to go from the +1 to the +2 ion. Additionally, we should say that the effective nuclear charge on the third shell is a +1. The effective nuclear charge on the second shell is 11 minus 2. It's +9. Because like I said, the second shell doesn't effectively shield the second shell. It shields the third, though. So what you're seeing is this complete confluence of various factors all coming together to say, if we as humans wanted to dig into an atom and get out electrons, the second you move to a new energy level, those electrons are not coming out easily. How not easily? Well, it doubles here, but then it's times 5. Then it's times 5, 6, right? This one is 10 times larger to take out the second energy electron than the first. So there's a whole idea, there's a whole world of digging into this electron structure and how you can change it once you start talking about measuring energy. But it all does come back to electron structure, atomic structure, and all the things that we've been talking about for the last few days. Thanks for watching.